Welcome everybody, you're watching Mr. Fugu Data Science. Today we're doing recursion. Thank you to the recent subscribers and viewers, I greatly appreciate it. Feel free to stop by, buy me a coffee, and show some support to help this channel. Let's get started. What really is recursion? It's when you have a function that directly or indirectly calls itself. And when should you use it? Consider if you have a task that needs to be broken up into subroutines, when the results of one step can be used in a previous step. Well, what are some of the considerations of using recursion? Well, if you have a loop that can achieve the same thing, consider using the loop. You have to take into account memory management. Depending on how nested the variables and parameters are, this can become a computation hog. Think about this. Each instance produces a new variable to store and use. So each instance is stored in memory as a copy, a new copy. Time can be an issue. Debugging can be difficult. You have issues where you can calculate redundant events, such as doing the Fibonacci sequence. 3 common issues with recursion: not setting up a base case. You're not progressing towards the base case. And the amount of resources that you're actually using for each function call outweighs any benefit. With that being said, you would say, well, maybe I shouldn't even use recursion. Not exactly. There's circumstances where it's beneficial. You have to consider memory allocation and your stack when using recursion. Remember that when you call a function, the memory is allocated on the stack, and a stack works by last in, first out. Remember the LIFO or LIFO principle that you would have seen in data structures. And there'll be an area or location where the data will be reserved on the stack. Now, when you call your function for recursion, a place in memory is stored with a copy of your local variables. Then, when the base case is reached, you remove the allocated memory and the value is returned. Think of using pop. So you're popping something from the stack. Otherwise, you continue until the parent function is reached. And you have to remember that this stack is consistently growing for each number of recursive calls that you have. So how are we going to use it? First, you need to establish your base case. You're doing this because you're trying to avoid having an infinite loop. You need to next make sure that you're moving towards this base case, because if not, you'll be deviating from the solution. Then you're going to have a call for your function, which is doing your recursive step. Essentially, what is going on? You're making a call to your function that is remembering where you were at for the previous step. Then you're moving forward to approach your base case if all goes to plan. Let's look at a couple examples of where this can fail. For instance, you could forget to add your base case. If we were summing some numbers and we forget to put a base case in here somewhere, for instance, we would have an issue because we wouldn't know where to stop. If we wanted to get close to the base case, the next example, what if we do declare a base case here and we have our recursive call here, which is calling this sum once again? You have to notice that we have an issue. We're never getting close to the base case because we're consistently increasing our values. So we're just raising our values and never approach the base case. You have to remember that as well. Remember, recursion is used to subdivide a problem into smaller subproblems to get close to some result that you're looking for. You could have issues where you're not allocating resources effectively, okay? You could arbitrarily start doing other operations that may be non-essential towards actually calling your recursive function, such as making print statements and in separate lists storing irrelevant data that may be unnecessary. So you have to be careful with that. Let's look at 2 examples of the Fibonacci sequence and consider iteration versus recursion to get an idea of what can go wrong. For instance, the Fibonacci sequence, we need to evaluate some form of a base case. We could start by something like this, all right? Because we remember that if we're dealing with a factorial, 0 and 1 factorial just equal themselves. And what essentially are we doing is taking the last step and the second to last step and adding those together. And this is what the sequence starts to look like when we print it off after a few iterations. Now let's look at some of the code. During the recursion process, we're going to start with our case of if it's less than 0, we need to input a new value. And we're starting with our base cases here, which are a little dubious, but that's what we're starting with to get the sequence going. And then we have to recursively call here to add our last step and the step before that together to get our next step. And if we time this for the Fibonacci of 30 going up to 30 values, we're going to notice that this is in the milliseconds here. When you start increasing this number number, let's say like 100 or 1,000, it will get huge in seconds. You also have an issue where when you're doing recursion, you have to consider a recursion depth. The more nested you go, the longer the recursion steps are, the more resources you're going to have and issues with your memory, and you're going to receive an error. That brings us to caching and recursion depth errors. We need to remember that caching is using a temporary location to store our data. It's good because the data that's accessed is fast. The problem is that memory is expensive, and if it's not in the cache memory, you have to decide where to store it, and this can be tricky. The amount of cache memory that you have is also limited, so you have to manage these resources effectively. There's something called LRU cache. Okay, and that's dealing with accessing recently used events for your data and getting rid of anything that hasn't been used recently. And it's a trick that you can use for recursion, which is hogging up your memory and your resources. And a benefit of using this is the fact that you're not having to restore or recompute every step of the recursion with this. So if you're using Python, it's good for you to call this LRU cache. It's a decorator that's allowing you to run the code from above, not run every instance, and speed up your process. You have to consider one thing though. When you're doing this, it's dealing with dictionaries, all right? And if you have a function, you have to make sure that whatever you're calling is hashable. When I mentioned you have this recursion depth exceeded error, which is really annoying, you could try importing something like this and put a number inside of here that's pretty big. You have to understand that this is affecting the way that your data types are being handled with your garbage collection. And the problem is that you're creating unnecessary copies, for instance, with your mutable objects. And lastly, something you should take into account, Python doesn't have a way to optimize tail recursion. For instance, tail recursion, just think of your very last step is calling your function call for the recursion, and you're not doing any other operations within your function other than setting it up to do the recursive call. So if we run the same function for the Fibonacci and use our good old LRU cache with our decorator, we'll notice that we're in the microseconds instead of milliseconds now, which helped us out because of this. Think about if we were using f of 5 for the Fibonacci sequence, meaning that we wanted to return the fifth number from the Fibonacci sequence, meaning that we have to go through this tree-like structure, and at each step we're splitting it in half and splitting it in half. And if you notice something, with the blue lines, this is creating our duplicates, and we're creating triplicates here. So your n-1 are creating duplicates from our f, and our n-2, which is these, is creating our triplicates. You could avoid this right here, this whole computation, if you set this up differently. For instance, you can use dynamic programming for this, but we're not going to get into that today. Let's look into doing some looping with the same thing. For instance, why would we use recursion versus looping? Sometimes you just have a situation where it's almost impossible or extremely difficult to run the loop, and it's more favorable to do recursion. In this case, looping would be far better. If we look at the printout here, we're doing the same type of setup, our initial values basically here, and we're iterating through our numbers, adding them together, and just doing an update statement and then getting the totals. While this simplifies our process and completely speeds it up, let's look at some time complexity and space complexity for the Fibonacci sequence to get some ideas real quick. For instance, in the recursive case, we end up with the big O notation of an exponential function with the space complexity being linear. And this is because of the splitting that you have for the branching, okay? And the n is coming from the function call itself. No matter what we do with the iteration, is going to be linear. And the great thing is the space complexity is going to be constant no matter what. Like I said before, if you wanted to make the recursion portion better, consider dynamic programming, and I left a link for this. As always, remember the code will be in the link and description below for my GitHub. We can look at another example of doing sorting a list. Here, the base case is kind of hidden, but it's inferred that it's either a 0 or a 1 for your base case being true. And then we're calling in the sorted portion to evaluate if our list is indeed sorted or not, to run through it if we haven't reached the base case yet. Now, I printed out two examples here to show you how this is working, and it's just evaluating this simply. We can look at doing merge sort, where the base case doesn't seem like it's a straightforward event, but if if anything is less than 1, that's where the base case happens. Merge sort is nice because at the division step you have a log n, because at each step you're cutting it in half. Basically you're breaking it up or dividing, partitioning your data in half, and then iterating over each one of those pieces. And when you're recombining, you're doing an n comparisons. So you have an n log n for your worst case scenario for the merge sort. The base case, you need at least 1, and the recursive step, you're running the merge sort on the left and right hand sides of your data. This right here isn't the actual code, just think of it as like how the algorithm is kind of set up, like almost like pseudocode. We're calling in our base case. We have our recursive calls here where we're trying to sort each side, the left and the right hand side of our list. Typically you won't have to do this motivation by hand unless you're taking an algorithms class, and you have to probably implement this as a class. Other than that, this gives you an idea of how this can be used in the real world and gives you a way to think about some of the scenarios you can have this come up and kind of how you should approach it. I did an example in a previous video where I had to parse some data, and I showed how you can use a recursion function to deal with some JSON data such as this, where we were looking to see, do we have a dictionary? Do we have a list? If we have it, run a particular function and iterate through it for each one of those, append everything together, and call our new formed list with our data. And in essence, what we were doing is going through each level of the nested JSON data and storing it as every single key with the dot notation, and then calling back our value that corresponds to it. Because when you're dealing with very nested data, sometimes you may want or need the full extension for what you're dealing with. Just depends on your circumstance. But I wanted to just express briefly some of the uses and ideas behind recursion and give you an idea of what to look for, what to avoid, how to implement, and I hope this brought utility to someone. Please like, share, and subscribe. And if you subscribe, turn on that notification bell. Hit me up on Instagram and Twitter. And if you thought this was useful, considering going to buy me a coffee and hitting up my name and help support this channel. I appreciate it. I'll see you in the next video. Bye.